of the ceremonies here. Trey, take it away.
Okay, thank you, Judy. Good afternoon, everybody that's out there listening. As Judy said, we're going to talk about the principles of exhaust filtration as it pertains to spray booths. So we'll just take about the next half hour and kind of go over that. So moving into our presentation, for CoilMet, in case you're not familiar, CoilMet, we sort of break our business up into three business segments. So our first segment is our core and catalog equipment, which, is most of the majority of the spray booths and powder booths and batch ovens and things along those lines that can come right out of a catalog, fit into a lot of operations. Then we have our engineered projects, or our EP group, which would handle things that need a little bit more engineering, inline washers, custom powder booths, custom spray booths, things, that would take just a little more engineering and thought than just a normal run-of-the-mill cookie cutter booth. And then what we're going to talk about mostly today is what revolves around our third business segment, which is the RP filtration products, which is a slit expanded paper, polyester backing. But today we're mostly going to focus not on the filters, but just the principles and some of the codes and requirements that the filters have to abide by. So to get into that, we'll kind of talk about the principles of filtration and what the actual filter does for our overspray inside our booth. So to kind of get everybody kind of up to speed in what we're talking about, the purpose of filtration is to just remove the airborne contaminants. So for us, that's overspray, particulate in most cases. Where our product line is mostly focused is around the 25 micron sizes, being because of the bell curve for particulate sizes. They can range somewhere between 10 to 100 microns. That mid-range that you're going to see, the majority of the sizes are around 20 to 40, we could say. But that's the sizes that we're kind of going to concentrate around, which if you see the little chart to the right there at 25, we're talking about visible particulates to your eye, right? So it's very obvious that paint overspray is a visible particulate. Depending on the type of application equipment that's being used, that particulate curve that I was talking about is going to change. So, if we're using a rotary atomizer, our micron consistency is across the board on an average a lot smaller in size. If we're using a conventional air gun, and let's say like an airless system, our particulate sizes are going to be a lot larger. So this plays an impact on us in the filter for our spray booth, because depending on the application, certain filters will perform differently than other filtration. So it's important to understand, how the filter is, what it's designed to do and how it responds to these different sizes of particulate. So there's 7 actual scientific principles of air filtration. We're really only going to talk about 4 of those today, because those are the 4 that most affect the type of filtration that we're talking about. The electrostatic attraction, sedimentation, and coagulation are more in HVAC, or if we were talking intake filtration and things like that, because they're trying to catch a lot smaller particulate. If we were trying to catch our COVID-19 friend that's kind of plagued us here recently, we would be talking more about those types of things. But today we'll concentrate on inertial impaction, which I'm probably going to say impingement at one time through there. So I kind of put that out there to let everyone know. Interception, straining, and diffusion are what we're going to concentrate today. So when we talk about inertial impaction, this is sort of exactly what it sounds like. We have a particulate flying in the airstream, and it just collides with our filter media. If you notice, the images on your screen are mostly representative of a polyester media. That's where we're going to do most of our actual filtering. The paper layering of our filter is there to sort of catch the rocks and the marbles, let's call them, the larger particulates, before it gets to our polyester, which is doing most of our actual filtration for the smaller items. So when we're talking about inertial impaction, those sizes are usually larger than 10 microns. Okay, so anything lower than that, they have a tendency to float. We'll talk about that around the with the airstream around the fibers. But inertial impaction is probably one of the larger reasons for filtration with the type of filtration that we're talking about, especially with the paper layering, because we're putting a honeycomb labyrinth in front of it so that we give it a better chance to actually collide with our filtration media. So just to kind of recap on that, just kind of talk about 10 micron, larger than 10 micron, right? Those are the things that we can see, dust, on up to, like the cross section of a human hair, which you can see is drastically larger than what we're talking about filtering. Interception is another principle of filtration for us, and it's really just a mechanism where the particulate follows the airstream around those fibers. And while it does that, our fiber is able to intercept it. There's some microscopic, tendons on those fibers. They're not perfectly round as our images show. So that particulate is able to maybe get caught up in some of those outer laying fibers. And this is usually done on a smaller particulate size, because it can change direction readily around the fiber, so it has less inertia, which would mean it would have less mass, so it means it's smaller, right? So, and this isn't quite as dependent on airflow or air velocity as, say, with impingement or inertial impaction. It's going to kind of behave this way, however it's happening, just because of the size of the particulate that we're talking about itself. And just to kind of recap, we're talking about some very small particulates, something like a light dust, an animal dander, down into where we're talking about bacteria and things like that. So, we're talking about a lot smaller sizes here. Straining is something that is very predominant in our type of filtration that we're talking about here, because we do see larger micron sizes. And what it is exactly what it sounds like. It's where our particulate is actually larger than the spacing between our filter media, and it just gets stuck between two members of the media, and it cannot go past it anymore. It really doesn't matter on the air velocity if it's fast or slow. It's just basically a size. Now, I do say this: if we have a filter that's been loaded to an excess, and your fan has enough capability, it will begin to start to pull these particulates through these fibers. And then hopefully, if that does happen, we catch them either with impingement, or maybe we can intercept them with another molecule, and it can stick to it just due to its viscosity. But this is done typically with particulates that are over 20, 50 microns. These are your larger 100. These are your larger microns here. Depending on the filter media that you are using, would depend on the size of particulate that would take to actually be strained out. So again, we're talking about visible particulates, and even up to like the diameter of a human hair, right? So that's really what we're talking about for straining. The last point that we'll kind of talk about on the technical aspect of this is diffusion. And diffusion is it happens when they're with very small particulate sizes. And what they're doing is they're just randomly moving around in the airstream, because they lack a lot of mass. So they don't really follow the airstream. They kind of flutter around in the air, sort of like a feather would if you drop the feather. It's just going in the airflow. It is sort of somewhat dependent on the air velocity. If the air velocity would be too slow, it would just eventually flutter down. But we have an ability to filter out these smaller microns through diffusion because of their path, because they're weaving in and out, which creates a larger path for them actually to maybe run in and either impinge or most likely probably be intercepted by our filtration media itself. And then that's just the kind of the way that we're looking at for diffusing and filtering out these smaller particulates. Now, these are small. These are 0.1 less than 0.1 micron, which would, and your reference here would be our COVID-19 virus that we're talking about, down in that size range, something that isn't easily seen at all with the human eye, or even at all. So those are the types of filtration principles that we'll cover in our little webinar today. Now, there are some regulations and some testing as it pertains to filtration for spray booths, not just for the spray booth itself, but for the actual filtration. So we'll run through those to kind of bring everybody up to speed on that. So the regulations for the filters themselves are the APA NESHAP standard 40 CFR part 63 6H. There is a more regimented test that tests down to a different testing method, as well as to smaller micron sizes, and that is the one that probably someone's heard as NESHAP rated, which would be the 40 CFR 63 method 319 for aerospace. So you'll hear people say that filter has to be NESHAP rated or something like that. They're all NESHAP tests, but the one that people refer to on that is when they're talking about the method 319, and we'll discuss those in a little more depth here in just a few minutes. The OSHA 1910 107 is a regulation that we follow as well for the filters as well as the spray booth, and the NFPA 33 is mostly designated to how we construct the spray booth at Colemet and the guidelines that we have to follow, but the filtration is part of that as well, and it really just refers back to the requirements of the 40 CFR testing and standard. So the NESHAP 40 CFR is a test that all filtration to be used as a standalone filter in a spray booth must meet the criteria of this test. And it says in the testing criteria that, and the standard, that it must be at least 98% efficient. So all a customer has to do is to be able to produce this test if requested by the municipality or the air quality or anyone like that shows that the filter being used is a standalone 98% efficient. If it wasn't a standalone 98% efficient, it would need additional stages of filtration before that air could be evacuated into the atmosphere. We make a product that is meant to be a sacrificial layer only, and it does not meet this requirement, nor was it designed to. It was just designed to prolong another filter because of the nature of the coating is one that can eliminate or wipe out a filter fairly quickly. So that was done for that reason. Now, this test for the 40 CFR is a little misleading, and it's done around an uncommon paint. The paint is a paint that is a very high solid. Sherwin-Williams Permaclad is the one that's been specified for this test, and it's done with a conventional spray gun. So the particulate sizes are very large. The coating itself has a very high viscosity, so it's collecting a lot of its own filtration just by sticking to it. The test itself is kind of hard for a filter, honestly, not to pass. But the test does give us some good information. It will tell us our efficiency through that coating, which means that once the filter has been weighed for what was sprayed versus what caught in the filter and the filter frame, and then what actually got caught on the testing filter media, and then that gives us a percentage, and that's the 98% that we have to keep. It will give a paint holding capacity. As we'll talk about here in a minute, that paint holding capacity, as well as some other information, can be a little bit misleading because of the nature of the test. So when you run the test, I've highlighted a certain section here. It'll give us our initial pressure drop, which is very handy. It'll tell us at 150 feet per minute, which the test has been demonstrated at, that our initial resistance through the filter is 0.03 inches of water column for this particular filter. I believe this is a 3200 series filter, which is 5 layers of paper and a lighter density polyester. And you see down at the bottom that our average removal efficiency was 99.65%. So we have achieved above the minimal requirement for this filter to run standalone in an environment. Now, this test is done, like I said, with a certain type of paint, a very high solid paint, which if you were in an application where a customer was spraying a waterborne or a clear coat, something that is atomized a lot more fine, especially with a clear coat because it lacks pigmentation, so it can be sheared into smaller micron sizes. The filter may not be, or probably won't be, 99.65% efficient. That's where it becomes very important to know the different types of filters, the different layerings of the paper, the different densities of the polyester, and the different combinations of those. And that's why we have a lot of models for that. And we'll actually discuss some of that next Tuesday on a webinar, kind of how to pick your filter and some case studies of some types of application where, certain coatings were used in certain filtration, and you can kind of see how the characteristics of the filter is different. So, but back to our test, it'll give us our paint weight of the kind of our holding capacity. But if you notice, the second line there says the final pressure drop of the loaded test filter. And this is where the test gets a little misleading because people ask all the time, when do I change my filter? And some people go to the test and say, well, it says right there that the loaded filter is 0.5 inches. So that's where you have to change it. The problem with that is the test is only conducted and concluded in one or two ways. It either hits 0.5 inches of a pressure drop and they stop the test, or it runs for a certain amount of time, which I believe, don't quote me, is around 28 minutes. And what that'll happen is we have some filtration that especially in our W series, where our initial pressure drop is around 0.03, but when the test was concluded, it's like at 0.18. So it never came anywhere close to the 0.5. It's unlikely to say that filter was loaded. It's just that it timed out at that time. So it's a little misleading when it comes to that. And when it comes to changing your filters, in your business and trying to sell filters, it really honestly boils down to what the booth itself can handle. So your booth was designed to move so many feet per minute. Let's say it was a cross draft. It was designed to move 100 feet per minute. If your filter load becomes so great that 100 feet per minute is become unachievable for the exhaust fan, then that is when the filters needed to be changed. The filters can handle more than a half inch of load. They handle easily probably around 3/4 inch of load before the filter itself begins to degrade or be pulled apart or something like that could happen. Most of the time, your fans on the spray booths are not designed for that unless they were set up for multiple layers of filtration. Most booths are around a half to 3/4 inch of static if Comet builds them. There's some other manufacturers out there that do it with less static than that. So that means that the filter load that is available is less, right? So the initial pressure drop is important to everyone, especially for getting longevity out of the filter. If we start with an initial pressure drop a lot higher, you'll see some filters in the marketplace, like some polyester filters that are all 100% polyester. They're going to start out at around 0.08 to 0.1 inches of water column. And they're going to run about the same efficiency that we are. What that means is that filter is already a higher resistance against the fan, which means that you're going to be able to load that filter for less amount of time than what a one with a lesser pressure drop is. So just to kind of let you understand on that test, if you need these tests in anything, we can provide them. They're in our literature as well. There's some graphs and charts that are very handy that show at different speeds through the filter face what we expect our initial static pressure to be. The question comes up is, how should the manometer be set, right? And the manometer, that fresh one, if we're moving 150 feet per minute through all the filter faces and we're moving our required amount of velocity through the booth, should be around 0.03 in this instant, right? So it gives you some information to check and go off of. Now this this slide here is a little bit of an eye chart, and the handout is available in the webinar. I believe you can just pull it right out of your control panel right now. It may go out as an email option after the webinar, but I want you to look at this because I don't want to spend a lot of time talking through it, but this is just a chart that was developed to kind of demonstrate the differences in a 98% efficient filter, which is, meeting the standard, and let's say a 99.9 or close to the 99.5 like we were looking earlier with our last filter. So what it's based on is if we had a filter face that was 80 square foot of filter face, right? That's multiple filters or blankets, but it's 80 square foot. And we had a booth that's spraying 1 pound of coating for 40 hours. And we just kind of worked the math through there. You'll kind of see if you look at the 98%, you're going to have 2% penetration. We're pretending that all the coating made it to the filter face, none of it stuck on the ground. And we do the math across there. But what it really equates to is after 40 hours of that, that's almost a pound of paint. And honestly, 1 pound of paint an hour isn't, a lot of paint in some applications for sure. So if you spraying 2 or 3 or 4 pounds an hour for 40 hours, now we're talking about 3.5 to 4 pounds of coating. Now that coating that got through that filter is going to go into the exhaust chamber. It's going to go onto the fan blades, right? And if you're spraying like a 2K polyurethane and that's getting through your filter and it's sticking to your fan blade, it builds up on that fan blade, and now the fan becomes less efficient because now the pitch of the blades are off, the curvature of the blades are changing, and then the worst thing that can happen is one of the blades breaks loose or the coating breaks loose from the blade, throws the fan out of balance, and then that is just a wreck waiting to happen, and that's very costly for a customer. Because of that, you'll come across some customers that are going to try to run the lowest priced filter they can. And the lowest priced filter they can usually means they're less efficient. And they say, they last a long time. Well, they do, because they're not catching anything but those rocks and boulders that are being thrown at them. But all of those smaller microns, those ones in the average curve of 20 to 30 microns, are going right through it and right into the fan blade or out into the parking lot, and they're putting free paint jobs on all their employees' cars, right? So that's something that it needs to be understood, you guys, when you're out in the real world, to see that, because sometimes that's all the filter you need because there's another filter behind it, and sometimes it's the only filter, and we have to be a little more cognizant of our efficiencies, and the impact it can have on other equipment down line. Now, the 319 aerospace test, currently right now, Comet and RP does not manufacture a standalone filter that is method 319 rated. Now, we have these filters and we use them on a daily basis in our spray booth. We just don't actually manufacture these in our plant. Now, we do those with bag filters, 2 and 4 pocket, 5 pocket bag filters is a standard that we would go to. Now, this testing criteria was created after the other test was created, because it was seen that it's not reflective of all coatings. And being that aerospace uses a lot of paints that have a hexavalent chromiums in them, because they're used in the military, because they're used as a rust inhibitor in those coatings, and they're very harmful to the environment and to people. So they generated another test that doesn't use a paint at all. It uses a potassium chloride and an acid to sort of simulate that overspray characteristics of a chromate paint. And those are measured down into a lot smaller micron level than what we're talking. We're talking in the 2 to 3 micron levels is where this test is really trying to focus. And what happens with that, because of the testing and the type of filter that's required, it typically dictates a 2 to 3 stage filtration system. And that's not because you necessarily need all 3 levels of filtration to meet that criteria. It's just that one filter that is actually rated to the niche out method 319 is a very expensive filter. And if you didn't have filters in front of it catching those larger particulates, it's going to blind out that highly efficient filter downstream, right? So like the Comet RP products and the W series products, that we normally run those as the first stage in our three-stage, system. And then we have like a polyester panel, and then we have our niche-rated bag filter in most instances. And what that does is that gives us a lesser expensive option to run in sacrificial layers so that we can catch those larger microns. We talked about our filter, catching things designed around 25 microns. So if we can catch those in our first stages and our second stage, then we're only seeing those smaller micron sizes hitting that higher efficiency filter, which is going to increase its longevity in production because we're protecting it from those larger items. So I hope that made sense to everybody a little bit. And I wanted to talk again next week on Tuesday. We're going to talk a little more about filter selection, go through kind of a case study, how do we pick the right filter for the right coating, kind of some things like that. Now, there's some basic guidelines we can go by, but it always changes based on application type, the style being used, how far is the process away from the filter media. All these things kind of play factors. But we'll talk about some of that next Tuesday, and hopefully, get you guys geared up a little better for what you can see and how to select the right filters. So at this time, I'm done. We can go through questions.
All righty, Trey, right now we don't have any questions, but I just wanted to open it up to anybody who does have a question. Please, on your control panel, there is a question bar. Go ahead and type in the question, and then we'll present that to Trey for an answer. So please take a minute if you have a question to fill it out now. Trey, you must have done a great job so far because there's not a lot of questions.
Well, or put everybody to sleep, one of the two.
We'll just wait here another minute or two. We've got 2 minutes yet before the presentation's over. The one thing I want to mention is that Trey did mention that we do have the handout that is included right there on your control bar as well. So you'll see that. And then let's see, we do have a couple questions coming in now. The slideshow, it's not going to be emailed to you as if you want to. You can just click on that right on your control panel where it says handout. The handout is included there as a PDF, so you can download that. Dave, thank you. He thanks us for the presentation, but other than that, it doesn't look like we have any other questions. There will be a short little survey coming out about an hour or so after this presentation, just asking you if you wanted to give us some feedback on future topics for presentations, as well as what you thought of the presentation. Trey, I guess we do have a question that came in. What is the MERV rating?
Okay, so MERV rating is done with a different test. It's done with the ASHRAE 52.2 test, and that is mostly seen around intake filtration. We're not required by the standard for paint booth exhaust to create a MERV rating. Now, if I was to just speculate, a MERV rating, you're talking about one that's probably 14 to 16, 14 to 12, somewhere around in there in a MERV rating. But it is a different test that's done by fractional efficiency. So it actually takes the micron size, of the particulate, and then it says the filter filters out a percentage of that micron size, and then it does that for all of them. But currently we don't have any exhaust filtration that has a MERV rating.
Well, I think that was it, Trey. There's no other questions that I see. If anybody does have a question, please feel free to email that question to us at marketing@colmetsb.com, and we will make sure to give you an answer. And it looks like, just checking again, we do have one more question. What would need to figure out how much air is being moved by a paint booth for those who don't know that information?
Okay. The best way that I have found to do that on the filter side as well as on the spray booth side is I like to take either an anemometer or a hot wire, which is actually what I prefer to use, and I measure the air velocity at the filter face. And so if you just visualize a 10 by 10 area of the filter face, I'll do 9 different readings and then 9 different locations on that filter face. And at each of those locations, if you visualize a 20 by 20 cell, I do 9 readings at that cell. And then I average all those out, and I just do the math to say the booth is moving, X amount of feet per minute. That's the most, I guess, accurate way that I have found to do it. You can stand in the middle of the booth with your anemometer and try to get that, in a cross draft 100 feet per minute. It's a little tough if you visualize like a pressurized cross draft and you have tower plenum. So you have an intake on one end that's in a tower, both sides of the corners of the booth. You have an exhaust that's on both sides of the booth. You'll see even in a pressurized environment that air will travel majority along the wall. And you can go over there and you'll get a higher reading possibly than 100. As you move across to the mill, you may not. In some of those instances, if you don't want to take the time to, measure the filter face, pardon me, I had a cough there. It's not a COVID incident, but you'll see if you put a part in there and take that reading, the air will begin to profile around the part. And sometimes that's an easier way to calculate that air movement through the booth without going down and making all of those readings at the filter face. But by far the most accurate way to determine that is at the filter face.
Well, thank you, Trey. We do have another question here. It's actually about the future webinars. Just wanted to let everyone know they were asking about an invitation for the next upcoming webinars. That was all links to all the webinars, which includes this Thursday's presentation on sizing a booth properly, that invitation, as well as next week's filter presentation that Trey was talking about. And lastly, our 4th presentation currently scheduled is on the NFPA and OSHA requirements. All those links to all those different webinars was included in the initial email. You simply click on that link, and then you can go ahead and register for any of the seminars you want. There's a different link for each webinar. If you didn't get that, or I'm not sure how to do that, please send me an email at marketing@colmetsb.com, and I'll make sure that you get any of the links you needed for the upcoming webinars. And I think that is actually it, Trey. It looks like we've answered everybody's questions. Thank you so much for attending today. Thank you for attending, and this will conclude our webinar. Have a great day.